the giving that thing. There you go. Okay, so everybody ready? All right, it's Monday. It's Monday morning. We're going to talk about fission first, all right? It just so happens that some of the bigger nuclei, some of them, not all, some of them are very fissionable, okay? Of uranium, if you look over here, the average mass is about 238, because probably 99 out of 100 of them are probably around 238. There's many isotopes of uranium, but the average is 238. But if you could separate the isotope U-235, that's the fissionable one. That's the one that will split the easiest, okay? So if you hear about a fissionable isotope, it means it would tend to split. And how do we get them to split? We fire neutrons at them. And neutrons can come from another radioactive source, all right? So anyway, what I want to do is, here's an equation right here. So we start with uranium-235, and we bombard it with a neutron. And what happens is it actually splits into something much smaller. These are not even close to the size of uranium. And I'm not saying they're actually even, so I might say split. It's not absolutely exactly in half, but it is two lighter nuclei. And then it gives off 3 neutrons and a bunch of energy. And then what happens to the 3 neutrons? If there's another uranium-235, and there'll be a bunch of them, it's going to split, and it'll set those off, set those off, set those off, and that's called a chain reaction. Now, if you can have a chain reaction, and it takes place in maybe 1/100th of a second, or 1,000th of a second, then you have a bomb. You have a bomb, maybe. Now, here's and I don't. Your book didn't have this, so I'm going to show you real quick. Think about physics for a minute. Remember how they had that lesson about a round object has the most amount of surface area per volume of any object. But what happens when the radius gets bigger? Like, what happens? Do you remember the physics lesson? So if the radius gets 2 times bigger in a sphere, what happens to the surface area? If the radius gets 2 times bigger, what happens to the surface area? And it doesn't get 2 times bigger, it gets what? 2 squared. Is that right? Okay. Do you remember that? And what happens to the volume? Not 2 times bigger, not 2 squared, but 2 cubed. Everybody get that? Okay. So anyway, if I had a little ball of uranium-235, and then I had one that had twice the radius, it would have 4 times more surface area, but it would have 8 times more stuff in it. Get that? Okay, so here's the theory. If you have a little ball of uranium-235, you're not going to make a bomb because it has so much surface area per volume that the electrons, they can leak out and they won't go in and start a chain reaction with some other ones. There's enough neutrons that leak out, but as you get bigger, then a certain amount will leak out. But compared to the amount in there, you can't get enough of them to leak out, and a chain reaction will take place, and you'll have a bomb. Now here's a word. You could have what they call subcritical mass. Subcritical mass, no bomb. And so when they make a bomb, they'll have a subcritical mass and a subcritical mass. Now, there are different ways of doing it, but if you wanted to, you could use a regular explosive, like dynamite or something like that. You could use a regular explosive and say, ready? I need to have a source of neutrons right here, right? Ready? Subcritical, subcritical, boom! Jam them together. Boom, boom, okay? Boom, boom. And because when you get 2 subcritical masses together, you would have a thing called critical mass. Have you ever read that before? Yeah. Critical mass is the amount that you would need that is potentially could create a bomb because it doesn't have enough surface area per volume to get rid of neutrons fast enough. So it would actually have a chain reaction and you would have a bomb. So you can have a bomb as long as these stay apart and they're away from this neutron. They can be sealed and then use conventional explosives to drive them together, make critical mass, and then you get a big bomb. You probably don't like me talking about this. You say, wait, what? Why are we talking about making bombs? Like, doesn't that kill like lots and lots of people at once? Yeah. But if you don't know anything about it, maybe I think you should know something about it. Think about that. All of us say we're good, aren't we? Are we all good? Wait, the Bible says none of us are good. And so why would we create a weapon like this? So, yeah, it took a lot of intellect to eventually figure out how this worked, but essentially we could use this for a weapon. And you could kill a lot of people in a very short amount of time. And even the ones you didn't kill, the leftover stuff could radiate the whole city for the next, few thousand years. Even Japan, a lot of people were killed with the bombs. But even within 20 years, 30 years later, even some of the children that were exposed that eventually had children, their sex cells a lot of them were mutated. A lot of their DNAs were messed up. And there were a lot of birth defects. And that's like the effect of a bomb, like 20 years after the bomb fell. And so it's some nasty stuff. Now, on the other hand, you can use fission to generate electricity if we can control it. This is uncontrolled fission. But if we want to control it, we could do it like in a power plant. I think they showed you a picture. I don't know if I have a picture of that. Do they have a picture of a power plant in here? Oh, here's a picture I should have shown you. In this article, it showed how lots of escaping neutrons here, but not as many, more escape, but not per volume. And then here's your subcritical mass, and that's what you're reading at in your thing. Now, okay. EJ, you said you were the expert on nuclear power plants, is that right?
Yeah, expert.
Well, no, but the last thing I read is the United States around, I don't know, what's the percent of electrical energy produced by nuclear? Do you know?
I'm not sure about America, but I know that there are a lot of countries in Europe that use mostly nuclear energy. So I think that's about as France gets like 70% of this.
70? Okay. I don't know if ours is at 10 or...
It's not super high. It's more than wind and solar, but it's not.
Oh, yeah.
Wind and solar is like 3%.
So, and it depends on if you go to, like I said, near Lake Michigan, I hate the idea that there's like 15 nuclear power plants right next to the greatest freshwater source in the world. But at this point, as long as nothing happens, I guess we're okay. But I don't know, it seems like it's a big chance we're taking. All right, so what happens here is we have fuel rods. They have uranium-235 in there. And then we have these other rods. It's in water. And we have control rods. They're probably made out of cadmium. They absorb neutrons really well. So you got uncontrolled fission going on, and you put these little control rods in there, and they start sucking up the extra neutrons. Then it slows down the reaction. Hey, we need some more heat. Too much. Okay, so we can actually control fission reactions. But the problem is, after a while, the fuel rods get spent. Have you ever heard that? Spent fuel rods. Okay, so then they have a lot of radioactive stuff in there, and they're not producing enough heat, so we need to replace them with fresh fuel rods. Now, remember that this water source here is going to be radioactive. So we don't want that water to be the one that pushes our turbine. So this is called a heat exchange. Get that hot water here, and it's radioactive, but it never comes in contact. Only the heat gets transferred, and then that water gets really, really hot, turns to steam, and then I push it through a turbine, and the turbine has little blades on it, and you turn it real fast. It turns the generator and make electricity. Same thing with Duke Power. Duke Power burns coal. Coal heats up water. Water turns steam. Steam turns the turbine. We do the same thing. So you could use the same idea there. All right. I do want to show you how much. Do you remember? I can't find that figure. There's a figure there. It tells you. Oh, here it is. Here it is. Sorry, that's what I'm looking for. 1 kilogram uranium. And by the way, uranium is really dense, so a kilogram is not that big for uranium. Uranium kilogram is about that big. It's small. 1 kilogram of uranium yields more energy than what? What? 30 freight cars of coal. You could burn 30 freight cars of coal and produce the same amount of heat energy as 1 kilogram of uranium. So nuclear energy is way beyond the scale of chemical energy. Because burning coal is a chemical reaction, isn't it? It's not a nuclear reaction. All right. Anyway, we talked about what a water cooling tower was, but I want to talk about something here. Your book. I'm trying to think which way your book does it. Yeah, I think your book. Yeah, here it is. I'm not really using your book right now, but I want to show you. This is the same graph that person did on his video. Can everybody see that graph? This graph tells you why fission and fusion works. It doesn't make sense to you. First time I heard it, it didn't make sense to me. But if you took the exact mass of like 6 protons and 6 neutrons, it would be a little over 12 AMUs, exact. But when you put them together in an oxygen nucleus, they only weigh about 15.99. And that didn't make sense. If I measured some marbles individually and I put them together in a bowl, wouldn't they weigh exactly what they did individually, added up? And they call that a mass defect. There's a defect. There seems to be missing mass. Where's it at? How can it possibly weigh less than it's supposed to? What is it? Right. So E equals mc squared. First of all, the most ingenious thing about E equals mc squared, and this is in the early 1900s, was that right there, equals. He said energy and mass, they're the same thing. They're the same thing. What? And we actually know how to change mass into energy. Fission, fusion, bombs, that kind of stuff. We can do that. And we can, a little bit, we can actually see, we have evidence that energy, just energy, can change into matter, can change into mass. We're just not really good at that. And you guys are much, much younger than me. So sometime in the next 50 years, it's very possible that we'll learn how to change energy into matter, into mass. And if we get really good at it, then you have things like on Star Trek where they have replicators and I'll have a Earl Grey tea, please. Anyway, and then all of a sudden energy is changed into matter and they arrange the matter into patterns and there's a cup, there's a tea, everything like that. I don't know. That'd be pretty neat. Yeah.
I've read that they're finishing up a power plant in a fusion plant in America called ITER, and they're supposed to have predicted sometime around the 2040s to have
2040s?
To have it, yeah, and then 2050s is supposed to be commercially available.
For energy production?
Yeah, I think so.
Would it be like home?
I would think it would
You could
be
run every
similar
car?
to a power plant like what they're doing with fission, but I don't know.
It's very
That's
possible
where
in
we're
your
at.
lifetime that you could have a home, every home. We could actually go anywhere on the planet. Hey, I don't want to go up there. It's so cold all year. Well, here, take this pellet with you, okay? Here's enough energy for you the whole year. All right, so you could live up there and you never get cold because you have energy, right? Or use energy to run your appliances. You could live anywhere on the planet. We could go to the driest place in the world and change something, get water from something else. So energy's always been the biggest hurdle for people living somewhere. When we colonized the United States, where do they always go to first? Rivers. Why would they want to make cities? Why are all your big cities, why were they along rivers? Energy. And they could use mills, right? Sawmills, grain mills, like that, and they could use energy that way. Well, let me show you. This picture here is the opposite of this one, okay? So it all depends on how you want to look at it. Right here, this says atomic number versus mass per nucleon. Now, I know you're not going to like this, but if you are a hydrogen atom, the mass per nucleon, and guess what? There's only one proton there. The mass per nucleon is really high. You're kind of like what you're supposed to be. But what happens when you get to something like lithium? What's the mass per nucleon? Well, it should be the same. The protons should weigh the same. The neutrons should weigh the same, but they don't. They weigh less, don't they? Where's the missing energy? It's been converted into, where's the missing mass? I'm sorry. It's been converted into energy. What kind of energy? The energy to hold the nucleus together. What was that fancy word they used? Start with a B.
Binding energy.
Binding energy. So you look at this graph. This is a graph of binding energy. So here, right? As the mass per nucleon decreases, what did you do with all that mass? I'm using it to hold me together. So where's the most stable elements? They're right about here. See that? Iron. Iron is one of the most, it's the most stable nuclei we know of. Now, if you look at the opposite reaction, if you look at the opposite graph, instead of saying mass per nucleon, it's binding energy, right? It's the opposite. The more mass that was seen to be missing, the more energy is here for your nuclei. Do you like this graph better or you like the other one better? I guess it doesn't matter, but I'll do this one because most books have this one, right? Here's what happens. Let's look at fission, right? Here's a U-235. If you were to split it and turn it into an element that was not as big, see these? Then what would happen? The binding energy would increase. I'm sorry. The amount of binding energy here is here, and if you split it, it comes here. So the difference here would be how much energy might be given off in a nuclear reaction. Hello. Okay, thanks. Where's that? Oh, yeah. So the difference of energy here would be how much energy you could give off in a fission reaction. And what he was saying in the video is the difference between here and here is kind of big. It's a lot of energy. But what about here? What if you change and put some of these together and turn them into here? What's the look at the difference in energy there. It's huge, isn't it? And so you can get more energy from fusion than you can from fission. But this graph explains fusion and fission. All right, so let me see if I can figure this out here. Let's see. So I hate to use this chart because this is the opposite graph of the one you have in your book. Does this make any sense to you, this one? So if the mass per nucleon here, it seems to have more mass than these would, then again, the most stable isotope should be somewhere around iron. And that means that iron would not want to undergo, okay, let's do some fission with iron. That won't work. Let's do some fusion with iron. No, that won't work. It's the most stable nuclei we know of. Yes?
So do a lot of stars stop at iron?
Yes. Now, I've read a couple theories about that. How do we have any elements that are past iron? And some theories talk about when stars are forming, or when stars explode, a nova. They think that all the big elements came from something else, stars exploding, or where stars are born. But really, fusion itself and fission stars should stop at iron. Anyway, if you want to read, you can. I don't know I don't know which one is the most preferred theory about where elements past iron came from. I'd have to look. I'm going to research that a little bit more, I guess, because. But one time they talked about where stars are born. That's when you end up having when stars explode. That's when they can have elements that are past iron. All right, I'm not going. And again, I'm not using the book. They have some of the mathematics in here, and they actually have some mathematics where you put in an equation E equals mc squared, and you change it into joules and stuff like that. We're not going to do that. But I want to. Let's go now. Let's go over here. Okay, here's something that you may have read before. When we were doing the Manhattan Project in World War II, okay, I don't know how we kept that secret. Because there was an entire town, a huge number of employees, and they had to move their families there, and they stayed there, and the stores are there, and they had Little League games there, and they had barbers there, and you live there, and that's where you live. You're not doing, you can't tell anybody what you're doing. And back then, in the 40s, People were pretty good at that. They really did. They trusted the government absolutely 100%. I don't know today. It's unfortunate. But when the government said to do something, you knew to be part of the community, you would do it. I remember one of my favorite baseball players, Mickey Mantle. I didn't find out till much later that I just thought he was like a hero. I didn't find out till much later about all the stuff he did and when stuff he shouldn't have been done. But and that was the first time as a young kid I thought, wow, I didn't know that. But why wouldn't I know it? Because back then, if they told the press, don't write that story, they didn't. Because the press knew that we want to try to keep this image of this person a certain way. Now that would never happen. They would sell more magazines if they told the story. They even make up stories sometimes. But back then, I guess first time I didn't understand that, where I didn't think there was anything wrong with Mickey Mantle. But there were a lot of things he did that he shouldn't have, and we all are sinful. So it's not like he was more than a sinner than me. Okay, so where's I at? Where was I at? What was it?
Manhattan Project.
Oh yeah. So when they were doing this, it took years. You had to make the factory, and then you had to separate these isotopes. So you had to bring in tons and tons of uranium rocks that looked like plain old rocks. They had a Geiger counter, click, 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 click. They're really radioactive, okay? And they had to crush them up, and then they had to, I don't even know back then, I know now they vaporize it. They vaporize it, turn it into gas, and they rotate it in a centrifuge, and then the heavier isotopes go here, and the not so heavy here, and then they start separating the isotopes until they get U-235. But it took over 2 years to make two pieces of uranium-235 for the bombs. Now, back then, of course, you don't going to tell the world, hey, we only have 2 bombs. Okay. We're not going to tell anybody that. You drop the first one, and you say, oh, but we don't have another one like that. Oh, yeah, we do. We got more of them. All right, we surrender. But nobody knew that we didn't have like 20 of those bombs, and that was important. It was still taking longer to get that much material, to gather that material. Even today, we have places that make fissionable stuff, and if they have some kind of accident in that place and it's closed down for 2 years, that's going to put us in a precarious situation. If these other countries are still producing all this fissionable material and we're not, they're going to have a certain amount of control. And because right now, why don't every country blow everybody else off the planet? I hope they never do that. But right now is a balance of power, isn't it? Sort of, a little bit. And so the threat that your own country would be wiped off the face of the earth is enough to defer you, right? So, all right, I'm not going to do that because I know what you would do if I do that. But what if you knew that you were down to, I don't know, if you're down to X number of weapons and you couldn't produce it, I'll just wait 2 years. I'll wait 2 years till you're really down, and then we'll threaten you. And then, anyway, I don't want to talk about, it's kind of getting me down just talking about this kind of stuff. It would be nice to get rid of a lot of this stuff, but it's really weird when you talk about politics. I remember at one time Russia had this many nuclear rockets, warheads, and we had this many. They said as long as they're pretty close, the same. And then what happened is, here's how political it got. They said, well, we want the same number as you do. But what was happening is the Russians were making, they're called MIRV, multiple warhead rockets, okay? We want the same number of rockets. Well, this rocket had 4 nuclear warheads in it. And what it would do was take off, and it would split and go to 4 different cities. Well, see, they thought it was fair to have, you have this many, you have 2,000 rockets, we have 2,000. But they had more, see? Each one of their rockets had 4 warheads in it. And we thought, that's not fair. And yeah, it is. You get 2,000 rockets, we get 2,000. So you get very political and stuff like that. And I'm actually surprised. Right now, the best thing for you was the fall of the Russian economy. They were pouring huge amounts of money into their military, huge. And even the regular people, some of them, they can have a foodie, really. And that really collapsed their economy. And so that was probably the best thing. But I never underestimate Russia at this point. I believe that they're trying to build back, and they may be further than I think. And then we have China. China was nothing for a while as far as military. They're way up there. They're way up there now. Probably the worst thing that could happen is if Russia somehow stopped being enemies of China. That would be a bad thing, because then we'd have to have, I don't know. You know, I'm getting depressed talking about this. Let me talk about something else. At this point, I would hope that wisdom would come out, and that is not going to happen at all. I hope over your whole lifetime that no nuclear weapons will be dropped anywhere. I hope. I think that's why you want to learn about it. I would have people write about Hiroshima and Nagasaki. I would have you people read it and see the pictures, and you say, this is terrible. It was terrible. I also know that if they hadn't dropped the bombs, the war could have gone on for years, and probably the same number or more people would have been killed in conventional war. And then, I hate to say this too, that Germans, they developed rockets before we did. So if they had nuclear technology and rockets, they would have controlled the world. They would have. I threaten you. Do what we tell you to do. No. Boink. Washington's gone. Do what we tell you. No. New York, you're gone. And so I know you don't like the idea that we dropped the bomb. I understand that. But things would have happened. Other countries were very, very close to developing this. Very close. Oh, by the way, as a short note, it has nothing to do with this chapter. After the war, you had all these rocket scientists, right? Ever heard that? And they were really good. But what do they tell? What happens? Well, the Russians came in there and they said to them, this war, they're going to find you guilty of being a war criminal. Or you can come to our country and help us do our rocket program. And that's what we did. We did too. You can stay here and you'll be on trial and you'll go in prison the rest of your life. Or you can come here and we'll give you almost unlimited funds and you can help us start a rocket program, like Wernher von Braun. Wernher von Braun started NASA. Where was he coming from? He was a German rocket scientist. Our space program started with rocket scientists from Germany. And whether you like that or not, and it's true, many of those scientists, they knew that threat of their death or their family's death, they were going to have to do what they were told to do by the Germans. And you can say, well, they just did what they did. But I don't know, you got to be careful. How far do you go? Whose fault is it? You know. Okay, all right, let's do another one. Let's do over here. Let's do fusion. Okay, now, fusion, how in the world do you get like hydrogen to want to run into hydrogen? When hydrogen has a positive proton, and when they get close, what's going to happen? They're going to repel each other, aren't they? You'll never get them to come together. Well, you will if you can put them in enough energy. If you get hot enough pressure, you can do that, and it takes a special place for fusion to take place. But here's what, this is fission. Let's go with fusion here and see if you can understand this equation. Oh, by the way, here's it says 30 liters of seawater. That's not very much, 30 liters. It has 1 gram of deuterium, and if you were to fuse it, it'd be equal to 10,000 liters of gasoline or 80 tons of TNT. That's like 30 liters of water has enough deuterium that you could have a fusion reaction, and that would be equal to that much energy. So there's a huge amount of energy in fusion. Now, everybody take a look. This is deuterium, isn't it? And what you're going to do is try to get it to fuse with another deuterium, and it would form helium-4 and a neutron. Or you could get deuterium and tritium. You could do that. That's another type of fusion like that. Wait a minute, all those fusion, they even, at this point, are trying to accelerate particles so fast. They're trying to accelerate them in particle accelerators. They're even trying to things like, let's try to see if we can slam a calcium atom into a uranium. And then maybe we can make an element that's way beyond here. Maybe we can make element 120. Maybe we can make element 130. And so that's another type of fusion there. Okay, well, hang on just a minute. Let me see here. How many? Let's just have about 1 minute of questions. I know I didn't do the best job on that. What questions do you have about fission versus fusion? If we could do fusion, and it's not that I have to use the salt water, but we have a lot of water on this planet, don't we? We could have almost unlimited energy from that. Yes.
So, I know that it's pretty hard to do something as small as hydrogen without heating it up. But if you supercool hydrogen fusion reaction, wouldn't that take energy away from the nuclear forces that come from?
Super cool. Usually, supercooling means that the particles have very little kinetic energy. So that means that has to do with their kinetic energy or their temperature. So what we're trying to do is try to get the energy that holds nuclei together. If we want to fuse something together, we want some of that matter to be changed into energy, binding energy.
But wouldn't taking that kinetic energy out of a atom, wouldn't that reduce the nuclear energy as well?
The only problem is it wouldn't reduce the nuclear energy, but if I want something to fuse into something, I'd have to crank it up again. I'd have to connect the kinetic energy up behind. But I could have cold uranium 235. I'm not sure it would make any difference. Cold uranium could still be split because it's the nuclear energy of it, not the kinetic energy. That's a great question you've asked. I wouldn't cool it if I was going to undergo fusion. But I guess I don't see the problem with cooling it if you're undergoing fission though. So. All right, well, thank you very much. Tomorrow, we're going to talk about half-life. I'm going to do a couple of math calculations to figure that out. And then that's going to wrap up almost everything. And then we'll just take one day to do the leftovers.